So here, this particular topic is about the inverse trig functions. All right. So we're going to look at how we can prove the inverse trig functions. But before I begin, let me give a very big shout out to Mr. Rad, Mr. Enoch, and Mr. Mohammed as well. Right. So we look at how we can prove these inverse trig functions. You know, the inverse trig functions, they are about 5. We have the sine inverse, the cos inverse, the cot inverse, the cosec inverse, and the sec inverse as well. Right. So it starts from the sine inverse. Right. So let's look at how we can prove this particular one. So let sine inverse, right? The sine inverse be equal to y, right? So we multiply both sides by sine because we are dealing with the sine. So we have sine times sine inverse u should be equal to sine y. Now the negative sine inverse take the positive sign, right? So we have u equals sine y, right? Now we differentiate both sides. This side, we use the chain rule at this point, and then we differentiate this part as well, right? So we have differential of this over this should be equal to the differential of sine, right? And we all know that the differential of sine will give us cos y, right? Then we differentiate the inner function as well. Here we are interested in the dy dx, so we divide through by cos y, cos y. So we have this taken off this, right? So when we do that, then we're going to have dy dx equals du over dx divided by cos y. Now we can simplify this further to make our mathematics so impressive, right? So we have dy dx equals du over dx divided by cos y. Of course, this is over 1, right? So we can say that we have dy dx equals du over dx times 1 over cos y, right? So we bring this here so that we send this back here. So we have dy over dx equals 1 over cos y times du over dx. Right. So right here, we have cos over here. So what do? We look for a function that we can replace it with the cos. So when we look at this identity, we have sine squared s plus cos squared s equals y. So we do that substitution here. So we say that, but sine squared x, in this time we are using the variable y. So we say sine squared y plus cos squared y should be equal to 1. We are interested in the cos, right? So we divide, or we send the cos, maintain the cos here, then we send this here. So we have cos squared y equals 1 minus sine squared y, right? So we divide, or we take square root on both sides, and then we have cos y should be equal to 1 minus sine squared y, right? But earlier notice we said that sine should be u. So we have cos y equals 1 minus square root of 1 minus u squared, right? So we put this into this, then we arrive at the right proof, right? So we have dy dx is equal to 1 over the whole of this, right? So we have root of 1 minus u squared times du over the x, right? And we are there. Very easy. Now we look at the next proof, which is the cos inverse, right? We go through the same process, but this time we are going to prove the cos inverse, right? So So we prove the sine inverse. Now we are coming to the cos inverse, right? So we know that, as usual, our normal representation, let cos inverse of u equals what? Y. Now we multiply both sides by cos because we are dealing with the cos inverse. So we have cos here, cos inverse of u should be equal to cos y. Now we take the negative crosses the positive, right? So we have u is equal to cos y, right? So we differentiate both sides. This time we use the chain rule here, and then we differentiate this part as well. So we have differential of cos, as usual, is negative sine y. So we have negative sine y times differential of the inner function as well. And that should be equal to the u over the x. Now, we are interested in dy dx, so we divide through by sine y, negative sine y, negative sine y. So we have this taking off this, and we can say that dy dx is equal to the u over the x, all by negative sine y, right? Now we can simplify this to make sense more, right? So we have the u over the x divided by negative sine y. Of course, it's over 1. So we have the u dy over the x is equal to the u over the x times 1 over negative sine y, right? So let's do proper presentation here. We send this here and bring this here, right? So we can say that we have the y over the x equals negative 1 over sine y times the u over the x, right? Now let's maintain this here, call it equation 2, and call this equation 1, right? Now we are having sine, so let's look for an identity that we can replace this, right? So we use the first identity, which says that sine squared y, because we are using y variable here, we change the x here to y. So we have sine squared y plus cos squared y should be equal to 1. Now we are interested in the sine, right? So we divide, send the cos here, and then maintain the sine here. So we have sine squared y here, 1 minus cos squared y, right? So take the square root on both sides, and we have sine y should be equal to a square of cos squared, right? Now, let's name this equation 3, right? So we have sine here in terms of 1 minus cos squared x, right? So we put that here in place of this, right? So now, when we put equation 3 into equation 2, then put equation 1 and equation 3 into 2, then we can have dy over the x should be equal to, now the sine is now 1 minus, so we have 1 over negative square root of 1 minus, now the cos is what? U, right? So we have u squared times the u over the x. And that is it. Very, very, very simple. So let's do proper presentation here. So we have the y over the x should be equal to negative 1 over square root of 1 minus u squared du over the x. And that is the proof. Very, very cheap, right? Very, very easy. So what you have to know is that know the properties of the trig identity and know the derivative of the trig functions, and you are good to go. So let's add one more, that is the cot inverse, right? So we add the cot inverse see how that one too works. All right, so let's take the tan inverse here. So when we take the tan inverse, that one says that it equals 1 over 1 plus u squared du over the x, right? So we are using the left hand side to prove the right hand side, right? So here, what we do is that, as usual, our normal representations, this is tan inverse. So let's tan inverse of u equals y. Now we multiply both sides by tan, right? So we have tan times tan inverse of u should be equal to tan y, right? So now this takes up this, and then we have u equals tan y, right? So what we do is that we use the chain rule to differentiate this, and we differentiate this as well. So right, we differentiate this, and that will be du over the x, and that should be equal to differential of tan, right? So you know that when you differentiate tan, you are going to have sec squared. Now it is y, so sec square y. Then differential of the inner, right? And that is what we have here. We are interested in the dy dx, so we divide here by sec square y, sec square y. This takes off this, and then we can have dy over the x equals du over the x divided by sec square y. Now we can do proper presentation here. So we have du over the x times 1 over sec square y, right? Good. So bring the 1 over sec square y in front, then send this back. So we have dy dx equals 1 over sec squared y du over the x. So we name this equation 2, and then this equation 1, right? So now let's look for an identity that can fit this particular one, right? So when we look for an identity, we can see that there is a sec inverse sec property here, right? So we use the second identity, right? So we have 1 plus tan squared y should be equal to sec y, sec square y, right? So we fit the whole of this into this, right? We fit this into this, and then we can say that we are putting 3 into 2, 3 and 1 into 2, right? So now we can have dy dx equals 1 over 1 plus, you know that tan is already u here, so we say that u squared times du over the x, right? And that is there. Very, very easy, ladies and gentlemen. We have been able to prove 3 inverse trig functions, right? That is the sine inverse, the cos inverse, and the tan inverse. Our next one is going to be cot inverse, sec inverse, and then cosec inverse. Thank you very much for watching, and I'll keep you updating.